Our topic is differentiation of transcendental functions, and for this lesson, we begin with the logarithmic function. We shall consider the two cases of logarithmic function. So first, we begin with the natural logarithmic function, and then later we shall cover general logarithmic functions. The natural logarithmic function takes the form f of x is equal to the natural logarithm of x, or we can write it as y equals the natural logarithm of x. Now, its graph is shown here, and note that it passes through the point 1, 0. Given are some of the properties of the natural logarithmic function. First is that its domain is 0 to positive infinity. That is, you can substitute any value to x as long as it's within the interval 0 to positive infinity. So it has to be greater than 0. Likewise, its range or the set of resulting values for the natural logarithm of x is anywhere from negative to positive infinity. Now, this function is continuous, increasing, and is one-to-one, and that it is concave downward. So if you want to evaluate the natural logarithm of 2, so you may just use your calculator, you'll be getting the value of 0.693. Next, if you have the natural logarithm of 32, again, you may just use your calculator. This is approximately 3.466. And then the natural logarithm of zero point 0.1, this is approximately equal to negative 2.303. So now let's have properties of natural logarithmic functions. So if a and b are positive numbers and n is rational, then the following properties are true. First, the natural logarithm of 1 is 0. The natural logarithm of the product a times b is ln of a plus ln of b. The natural logarithm of a raised to n, so that's a power. This is equal to n times ln of a. Now, the natural logarithm of a over b, so that's a quotient. This is the same as ln of a minus ln of b. So these properties tell us that the expressions found on the left side is equivalent to the expression found on the right side. That is, whenever you have a product, ln of a times b, you can write it in its equivalent form, ln of a plus ln of b. Or if you have a quotient, ln of a over b, you may write this in its equivalent form, ln of a minus ln of b, or the power, ln of a raised to n. You may write it in its equivalent form, n times ln of a. So these properties are helpful later when we solve for derivative of this kind of functions, especially those that involves product, powers, and quotients, and even a combination of these types of functions. So let us try expanding several logarithmic expressions. Let us use the following properties. So if you have the natural logarithm of 10 over n, so we can apply property 4. That is, we separate this into the natural logarithm of 10 minus the natural logarithm of 9. So we use property number 4. Next, we have the natural logarithm of the square root of 3x plus 2. So first, let's rewrite this in the power form. So we have the natural logarithm of 3x plus 2. And then since it is a square root, so this will be raised to 1/2. Now, applying the third property to the natural logarithm of a power, it is said here that we can make the exponent a coefficient. So this is now 1/2 times the natural logarithm of 3x plus 2. So we used property 3 for this expression. Next, so we have here a quotient. We have the natural logarithm of 6x over 5. So this is equivalent to the natural logarithm of 6x minus the natural logarithm of 5. So we use property 4. And then notice that 6x here is a product. So we can further expand this using property 2, wherein we can separate 6x or ln of 6x into ln of 6 plus ln of x, and then we have minus ln of 5. So here we applied property 2. So let's have this last example. We want to expand the natural logarithm of x squared plus 3 quantity raised to 2 all over x times the cube root of x squared plus 1. So first, let us rewrite cube root of x squared plus 1 into, so first we write the numerator. So we have x in the denominator, and then we have x squared plus 1. So this is raised to 1 over 3. Now, first, we use property 4 to separate our numerator and denominator. So we have ln of x squared plus 3, so this is raised to 2, minus ln of the entire denominator, which includes x, times x squared plus 1, so this is raised to 1 over 3. So here we applied property 4. So we separated our numerator and denominator. Next, so for the first term, we have a power. So using property 3, wherein we can make the exponent a coefficient. So we have 2, and then we multiply it to the ln of x squared plus 3. Minus, so the next term consists of a product. So we will be using a property 2, but we have to make sure that we enclose this in a parenthesis so that we can distribute -1 here. So you have ln. So we separate these two here, these two expressions as ln of x plus the ln of x squared plus 1 raised to 1 over 3. So we use two properties here. We use property 3 for the first term, and we use property 2 for the second term. Continuing, we have 2 times the ln of x squared plus 3. We distribute minus here, so or so it becomes minus ln of x. So and then we have minus ln of x squared plus 1 raised to 1 over 3. So we just distributed our operation. And then again, we apply property 3 to our last term here, which has an exponent of 1 over 3. So this is 1 minus 1 over 3 ln of x squared plus 1. So for this last portion, we applied property 3. So this is now the expanded form of the given. So now let's consider the special number e. So perhaps you've already studied logarithms in your previous pre-calculus subjects or Gen Math subjects like algebra, and you would have considered the logarithm in terms of what we call a base number. So here, for example, common logarithms have a base of 10, and we write this as, so instead of ln or the natural logarithm, we use the log symbol. So this is the log of 10 base 10, and it is equal to 1. Now, in the case of a natural logarithm, so its base is defined using the fact that the natural logarithmic function is continuous, it is one-to-one, and it has a range of negative to positive infinity. So given the properties mentioned, it is important to note that there must be some unique real number x satisfying this equation. That is, the ln of that number x is equal to 1. So we're trying to find the ordered pair x1 for the natural logarithm. So what is that x that gives a y coordinate of 1? So this number is in fact denoted by the letter E. It is an irrational number, and it has the following decimal approximation. So E is equal to 2.71828182846. So irrational, meaning this is non-terminating. So therefore, for the function, the natural logarithmic function f of x equals ln of x, we have the ordered pair E1. So that is if you substitute e uh, 2x here in the natural logarithmic function, you will be getting 1. Now let's try applying the properties discussed earlier. So if we have ln of e raised to n, now property 3 tells us that we can make n, the exponent, a coefficient. So n here is our rational number exponent. So n times ln of e using property 3 of logarithms. And then we know that ln of e is equal to 1, so this becomes n times 1, and n times 1 is just n. So whenever you're solving the values of or evaluating ln of e to the n, the answer is simply n. So for example, if you have here the value of x is 1 over e raised to 3, then if you take ln of x, then the answer is just negative 3. If you have ln of x is 1 over e squared, this means e is raised to negative 2. So for the first one, this means e is raised to negative 3. So the ln of that value is negative 2. Now, if you take ln of 1 over e, so this means e to the negative 1. So using this property here, that ln of e to the n is just n, so the answer is just negative 1. Now, if you take ln of e raised to 0, the value is 1, because remember that the natural logarithmic function passes through the point 0, 1, and then ln of e raised to 1 is 1, and then ln of e squared is 2. And you can see the graph on the given figure. Let us now discuss the derivative of the natural logarithmic function. So we have here the theorems involving derivative of the natural logarithmic function. So u must be a differentiable function in terms of x. So number one, if you want to get the derivative of the natural logarithm of x, so it's ln of x. So the derivative of this is just 1 over x, where x is greater than 0. Now suppose we have a composite function. So instead of getting the derivative of just ln of x, we have ln of u, where u is, as mentioned, is some differentiable function in terms of x. So we need to apply what we call chain rule for natural logarithmic functions. So when you get the derivative of ln of u, this is equal to 1 over u. And then we have to multiply this with the derivative of u with respect to x. So we can simply write this as u prime over u. Let's have some examples. So for the first one, we want to get the derivative of the natural logarithm of 2x. So since this is not just x, it's a composite function 2x, ln of 2x, then its derivative. So recall the formula is u prime over u, where u prime denotes the derivative of u with respect to x. So here, u is 2x. So the derivative is equal to u prime. So the derivative of 2x is 2. So 2 over 2x. So this is our u prime, this one, and then over u, and that would be 2x. So simplifying, we cancel 2, so the final answer will be 1 over x. The derivative of ln of 2x is 1 over x. Next example, we have derivative of ln of x squared plus 1. So here u is x squared plus 1, and u prime is the derivative of x squared plus 1 is 2x. Therefore, the derivative of ln of x squared plus 1 is u prime. So u prime is 2x over u, which is x squared plus 1. Our next example, we want to get the derivative of x times ln of x. So this is a product. We have x times ln of x. So we need to apply product rule. And the product rule tells us that, so when we get the derivative of x times ln of x, so first we get the derivative of the first factor, and the derivative of x is just 1. And then we copy the second factor, which is the natural logarithm of x. So we just copy ln of x. Plus, this time we copy the first factor x and we multiply with the derivative of the second factor, which is ln of x. And from our formulas or the definition of the derivative of natural logarithmic function, the derivative of ln of x is 1 over x. So if we simplify this, we have the natural logarithm of x plus, so this one, we can cancel x. Therefore, we're left with 1. So the final answer is ln of x plus 1. Next, we have here the derivative of ln of x raised to 3. So here we're going to use chain rule for powers. Okay, because we have we're getting the derivative of a power. So the base is ln of x and its exponent is 3. So using that, according to the chain rule for powers, we bring down the exponent first. We bring down 3. We copy the base, and that is ln of x. And we put a new exponent, and that is 2. And again, according to the chain rule for powers, we have to multiply this with the derivative of the base. And our base is ln of x. So continuing, we have 3 times ln of x quantity raised to 2. Now the derivative of ln of x, again applying our definition, it is equal to 1 over x. So let's just rewrite this. We have 3 ln of x quantity raised to 2 all over x. Now let's try derivatives of natural logarithmic functions wherein we need to use or apply the properties we discussed earlier. So let's have y is equal to ln of x cubed times 3x plus 1 quantity raised to 5 over 2. So here we have a product. So we apply property 2 wherein we can separate this into a sum. You have ln of x cubed plus ln of 3x plus 1 raised to 5 over 2. So note that we are not yet differentiating. Instead, we are expanding our natural logarithmic function so that it would be easier for us to differentiate. So next, we apply the property 3. So that is the property for powers. So we can convert this into 3 times ln of x. So remember, for powers, you may bring down the exponent and make it a coefficient. So this becomes 3 ln of x plus. So the same thing for the next expression. We bring down 5 over 2. So that's the exponent. And we multiply this with ln of 3x plus 1. So this is the expanded form. And note that this is much easier to differentiate compared to the given. Now we proceed with getting the derivative. So we have dy over dx. So remember that we only copy coefficients. So we just copy 3 and we multiply it with the derivative of ln of x, which is 1 over x. Plus, for the next term, we just copy again the coefficient, 5 over 2. And we multiply with the derivative of ln of 3x plus 1. Now, for ln of 3x plus 1, we can consider u to be 3x plus 1, and then u prime is 3. So the formula for, remember that the formula for the derivative of ln of u is equal to u prime over u. So therefore, the derivative of ln of 3x plus 1 is u prime or 3 over u, which is 3x plus 1. So let's just rewrite this. We have 3 over x plus 15 over 2 times 3x plus 1. Another example, let's say we're asked to get the derivative of f of x is equal to the natural logarithm of x squared plus 5x minus 1 raised to 7 all over the square root of x plus 3 and sine x. Okay, so again, it is much more complicated to differentiate this using the formula for um, composite logarithmic functions, ln of u, which is u prime over u. So instead of directly differentiating the given, we are going to expand this first using the properties of the logarithm. So we apply property 4. We separate the quotient, the numerator and denominator. So this becomes ln of x squared plus 5x minus 1 raised to 7 minus ln of the product square root of x plus 3 times sine x. So next, we use property 3. For the first term wherein we can bring down the coefficient, it becomes 7 times ln of x squared plus 5x minus 1. And then for the second term, we have here a product. We can separate this. So instead of differentiating it outright, we will separate this into ln of x plus 3. Instead of writing square root, we'll just write it as 1/2 plus ln of sine x. So let's just distribute the operation. So this is now minus ln of x plus 3 raised to 1/2 minus ln of sine x. So further, we apply property 3 to the second term. So this is minus 1/2 ln of x plus 3 and minus ln of sine x. So again, we just expanded the given first. We haven't differentiated yet, but this time the expanded form will be differentiated. So our f prime of x will be, so we just copy coefficients, 7. So for the first term, u prime over u, so we write x squared plus 5x minus 1, that is our u, and on top will be the derivative of that, and that is 2x plus 5 minus, we copy 1/2. Again, we put u in the denominator, so that's x plus 3. On the numerator, the derivative of x plus 3 is 1 minus, we put the denominator, we copy u in the denominator, so that would be sine x, and on top, or the numerator, we get its derivative, so that's our u prime, and that is cosine x. So simplifying further, this is now 7 times 2x plus 5 all over x squared plus 5x minus 1. And then you have minus 1 over 2 times x plus 3. And finally, we can use the property for cosine x over sine x. It's equivalent to the identity. So it's an identity. It's equal to cotangent of x. So this is now our derivative. Now, it is also convenient to use logarithms as aids in differentiating non-logarithmic functions, and we call this process logarithmic differentiation. So even if our function or the function that we want to differentiate is not a logarithmic function, or as said here, it's a non-logarithmic, we can apply what we call logarithmic differentiation to make the process simpler. So for example, if we want to find the derivative of y equals x minus 2 raised to 2 all over the square root of x squared plus 1, where x is not equal to 2. So here we note that y is greater than 0 for all x not equal to 2. So ln of y is defined. So by taking the natural logarithm of each side of the equation, we will be able to differentiate this in a much easier manner instead of using quotient rule. So what we do is we take ln of both sides. So we write ln of y is equal to ln of x minus 2 raised to 2 all over the square root of x squared plus 1. Now, using the property of logarithms, we can expand this into ln of x minus 2 raised to 2 minus ln of x squared plus 1 raised to 1/2. So this is the same as 2 times the ln of x minus 2 raised to 2. I'm sorry, this is already ln of x minus 2 only. And then you have minus 1/2 ln of x squared plus 1. So this equal to ln of y. So again, our given is not a logarithmic function, but we took the ln of both sides. So it becomes ln of y equals ln of x minus 2 raised to 2 over the square root of x squared plus 1, and we will apply logarithmic differentiation. So continuing, we want to get the derivative of this function. So we're going to differentiate this implicitly using implicit differentiation. So the derivative of ln of y, if you remember, we're going to get dy over dx or y prime. So whenever we differentiate y, the one in the numerator, we're going to differentiate it implicitly. So we have to multiply y prime to its derivative. So the derivative of ln of y is 1 over y times y prime. So recall implicit differentiation. And then we differentiate the right side. So this is equal to 2. We just copy 2. The derivative of ln of x minus 2. Remember, it's u prime over u. So we put x minus 2 in the denominator, and in the numerator, the derivative of x minus 2 is 1. Minus, we copy 1 half. The derivative of ln of x squared plus 1. So x squared plus 1 on the denominator, and then derivative of x squared plus 1 will be on the numerator. This is 2x. So let's just simplify. We cancel 2. Therefore, we have 1 over y prime is equal to 2 over x minus 2 minus, so since we canceled 2 already, this will be now x over x squared plus 1. Now, since we're looking for y prime, the derivative of y, this is the original function. So we multiply both sides of the equation by y. So this becomes y prime is equal to y times 2 over x minus 2 minus x over x squared plus 1. And further, we replace y by the given, which is x minus 2 raised to 2 all over the square root of x squared plus 1 times 2 over x minus 2 minus x over x squared plus 1. So this is now our final answer. We solved it using logarithmic differentiation. It involved what we call implicit differentiation. This is our past lesson. So let's try another one. So let's say we have y is equal to um, cosine of x all over x squared plus 9x minus 10. So instead of differentiating this as a quotient, we are going to apply logarithmic differentiation, which also involves implicit differentiation. So we take the ln of both sides. Ln of y is equal to ln of cosine x all over x squared plus 9x minus 10. Now, we apply the property of logarithms. We separate the right side into ln of cosine x and then minus ln of x squared plus 9x minus 10. So we use the property for quotients. Now we differentiate. The derivative of ln of y, again implicitly, is 1 over y prime, or dy over dx. And this is equal to, so again, for the formula of ln of cosine x, we write u on the denominator, so that would be cosine x. And on the numerator will be the derivative of u, which is sine x, or negative sine x. Minus, so for ln of x squared plus 9x minus 10, so we copy x squared plus 9x minus 10 on the denominator, and on the numerator, the derivative of that would be 2x plus 9. So we now want to get y prime, so therefore we multiply both sides of the equation by y. So this is now y times negative, so we simplify sine x over cosine x into tangent x, minus 2x plus 9 all over x squared plus 9x minus 10. And then we just replace y by the given, which is cosine x over x squared plus 9x minus 10 times negative tangent of x minus 2x plus 9 all over x squared plus 9x minus 10. So we applied logarithmic differentiation to solve our problem. Now we consider general logarithmic functions, or those logarithmic functions with bases other than e. let's say we have logarithmic functions having base a. So the derivative for this kind of function, so first we have let a be a positive real number not equal to 1, and then u is a differentiable function in terms of x. So if we want to get the derivative of the log of x base a, the formula is 1 over ln of a times x, or the definition. And then if we want to have or find the derivative of the logarithm of u base a, then this is the answer. It's 1 over ln of a times whatever u is, and then we multiply it by du over dx. So this is now, again, a chain rule for logarithmic functions. So let's say we want to find the derivative of the logarithm of cosine x base 10. So using the formula, so here, our base a is 10, while our u is cosine of x. So using the fourth formula, we have 1 over ln of 10, and then u is cosine of x, and then we multiply it with the derivative of u, which is cosine of x. So we have 1 over ln of 10 times cosine of x. Now the derivative of cosine of x is negative sine x. So again, we can simplify this by noting that sine x and cosine x, we're not canceling them. Instead, we're going to write that as uh, tangent x. So we have negative tangent of x all over ln of 10. So this is our final answer. So let's have another example. So let's use this definition to solve for the derivative of the logarithm of 4x raised to 3 all over x cubed minus 1 raised to 10. So this is base 15. Now, the properties that we used for natural logarithms are also applicable for general logarithms. So if we have a quotient, we can expand this by separating the numerator and denominator by subtraction. So this becomes log of 4x cubed base 15 minus log of x cubed minus 1 base 10. I'm sorry, raised to 10, then base 15. So using property 4. Now we can use property 3, wherein exponents may be written as numerical coefficients. So this is now 3 times the log of 4x base 15 minus 10, the log of x cubed minus 1 base 15. And then we now get the derivative dy over dx. So we just copy the coefficient 3. So using this equation or this definition for the derivative of a general logarithmic function, so you have 1 over ln of 15, and then we copy u, which is 4x, times the derivative of 4x, which is 4, minus, for the next term, we just copy 10. So the log of 15, or log of x cubed minus 1 base 15, the derivative is 1 over, again using this definition here is ln of 15. We copy u is x cubed minus 1, and then we multiply this with the derivative of u, which is now 3x squared. So let's just simplify this. So we can cancel 4 here. Thus, we have 3 over ln of 15 times x. So we can just write x here minus, so here we can, on the second term, but there's nothing to cancel. So this becomes 30 x squared, or all over ln of 15 times x cubed minus 1. So this is now our derivative.